Hello. Is my voice audible? Hello.
Yes, sir. Yes, sir. Audible, sir.
Okay, so let us wait for I think 2 to 3 minutes and then we can start, right?
Okay, sir. Okay, sir.
Hello, so am I audible? Hello.
Yeah, audible.
Okay, so we will be starting the session. So before we start, can you please introduce yourself? So we will like to first start with an introduction and then we'll go into the session. Why don't you
Yeah,
introduce yourselves one by one?
yeah. This is Mr. C.H. Kumar, Assistant Professor in Institute of Technology, Bhimavaram, Andhra Pradesh.
Okay, okay, great. So anyone else? Just we will start with a brief introduction. So please introduce yourselves. Hello, am I
Yeah,
audible?
yes, yes.
Okay,
I am Mr. Devendra Devari from
okay,
Odisha, and I am the research scholar.
okay, okay, great. So how are you guys finding the course on power quality? So the first week has been there. So how was it?
Very good, sir.
So anyone else like to introduce or can share their experience of the first week, and then we will start. Okay, so I will be starting the session. I am Subhadip Chakraborty. I am will be the TA for your these sessions, and these sessions are specially designed to actually guide you through the problem solving techniques and also learn the concepts through in the process. So we are moving on to the session. So I will be just sharing my screen. So hope my screen is visible, right?
Yes, sir.
Okay, so we will
Yes,
be
yes.
starting, right? So, welcome everyone to the first live interaction session for the course NPTEL course on power quality. So, this is about me. So, I am Shubhadeep Chakraborty. I will be your TA for these sessions, and I am currently a PMRF scholar in the Department of Electrical Engineering, IIT Delhi, under Professor Bhim Singh and Professor B.K. Panigrahi. I did my masters also from IIT Delhi and bachelor's from Kalyani Government Engineering College. So the session flow, I have kept the session first with the introduction to the power quality, just a brief introduction so that you can recollect some of the concepts that you have learned in week one that has been taught so far, and then some standard terminologies and the power quality issues and their implications and the power quality standards and the monitoring devices. You have already covered these already in the week one, but some brief introduction we will keep, and then we'll move on to some fundamental concepts that will help you in solving the problems, and then we'll solve some example problems that you can refer to while solving the assignment problems for week one. So this will be the session flow. So coming to the introduction to power quality, so any idea, must be having some idea. So what is actually power quality and why everyone is talking about it? So why is it important? Just few answers if I can hear.
In
So
the
why
the
yes,
in the
yes.
distribution and utilization area, some of the problems identified like sag, swell, harmonics, and voltage disturbance, flicker. These are the problems observed at the level of distribution and utilization. we have to reduce these problems by using some of the compensation devices.
Yes, yes, yes. So
Problems
absolutely
can
correct. So
be
yes,
considered as a power quality.
yes, yes. So actually, what is happening here is due to these issues, which are effects of the power quality. Causes may be many. Causes may I will be coming to the causes and the effects, but their implications are quite detrimental, both from an economic and also operational perspective. That the power quality issues that you experience may sometimes damage the equipment or also have the potential to cause system failure, and also it may sometimes pose to be quite economically challenging while experiencing some power quality issues. So we'll come to that. So basically the term power quality is arising from two perspectives, one from the voltage quality issues and another from the current quality issues. So there may be voltage quality issues, which just one of the persons have shared that there may be voltage disturbances, and some may be of current disturbances, current quality issues. So both issues have their own implications and we'll learn about them. So these form the power quality challenges that we will be talking about. So understanding the basics of the power quality has its implication both in the voltage, amplitude and frequency. That is in the perspective of harmonics, that there may be some distortion in the voltage signals, voltage waveforms, and they may lead to some power quality issues. Also, this power quality has its implications in the power factor, operating power factor, and obviously it is also accompanied with waveform distortion. So we'll come one by one to these issues. So the voltage, coming to the voltage based power quality problem. So just as one of the friends shared that there may be voltage swell, that is sometimes we experience that the voltage at the point of common coupling, as you have learned, the voltages sometimes rise. The RMS voltage for some few cycles rises. So why they rises? That may be due to some disconnection of heavy loads that may lead to voltage swell. Some harmonics may appear due to connecting very nonlinear loads at the point of common coupling. The interharmonics may also appear. The voltage unbalance issues, the flickers, all these you know because you have learned these in the week one, but we will see their implications, right? The current based power quality problems, like they may lead to voltage regulation issues because heavily loads with drawing heavy currents from the point of common coupling may lead to voltage regulation problems. So point of common coupling means where the either at the distribution level or at the generation level we may talk. The point of common coupling is referring to some points in the three-phase network where you connect the loads, right? So maybe this is the generation side and this is the loads are some auxiliary loads may be connected. So these may be some auxiliary loads, not only at the distribution side but from the generation side also. Some point of common coupling are there, and the generation side has some impedances. So if the load draws some high currents, then you can see the effect on the point of common coupling voltages. So this current and voltage quality actually complement each other. So if there are current quality issues, they will ultimately lead to voltage quality issues. So both are important, right? Then coming to the sources of harmonic distortion that we were talking about. So maybe due to you have connected some nonlinear loads. What means by nonlinear loads? That some rectifier based loads or some electronic loads which has some power electronic components in it, all are non-linear in nature because they are not linear components, so they draw harmonically distorted currents from the source. And as we have discussed, just due to the drawing of the harmonically distorted currents, there arises some current quality as well as voltage quality issues. There may be some natural reasons which may also lead to power quality issues, like for example lightning. If lightning is there, sudden faults may happen and some lines may get grounded, so they may also lead to voltage quality issues. Electric arcing, so there may be forced or unforced reasons, that is natural. So both reasons can lead to power quality issues, and these are the actually implications that that on the power system that they may lead to equipment damage. How I will discuss one by one. They may lead to efficiency loss. They may lead to derating of the individual AC components and resonance issues. So I will come one by one. So implications is like failure of capacitor banks, increased losses in the distribution system, noise, vibrations. How they are arising? Actually, for example, let us assume there is some voltage unbalance. So if you feed unbalanced voltages to an induction motor load, for example, then it will lead to noise. Then it can lead to torque ripples. And for electromechanical systems, it can cause losses, because these harmonics, actually, these harmonics may lead to losses. How? Because, for example, you have a polluted current, right? So let us, for example, you have a polluted current like this. So these currents can be divided into fundamental, and then third, and then fifth, and then so on, like that. So we can decompose it into harmonic components. So if the voltage is having purely sinusoidal waveform and the current is having distorted waveform, so this is the voltage and this is the current. So we know one point, that power is contributed only because of same frequency of voltage and current. That is, for example, 50 hertz. Now you have voltage at 50 hertz, for example, and current at 50 hertz, then 150 hertz, because it has harmonic components. So third, fifth, seventh, all are there. But active power can be, I will also prove it in the upcoming slides. Active power can be achieved only from voltage and current of the same frequency. Otherwise, active power will be zero. Between, if someone asks you 50 hertz voltage component and 150 hertz current component, what is the active power? Then we cannot draw any active power from them. So can one of you tell me that what is the issue? Because anyways we are not getting any power from 150 hertz current component, that is third harmonics or seventh harmonics. Then if it is not causing any power loss, then what is the issue with the current quality, current non-linear nature of the current? What is the issue? Can anyone tell me? You can open your mic, and then I want this session to be interactive, because you have already gone through week 1. So you should gain something new from it. So can anyone unmute and tell me what is the issue with these power quality problems if the current is distorted? Because we are not getting any power loss for the third and fifth and seventh, all those. If voltage is purely sinusoidal and current is, for example, distorted, what is the issue?
Sir?
You can unmute and tell.
Yes, sir. But when you have the resistive load, we can have the voltage and current frequency will be same. When it is resistive load, we have
Yes.
inductance load and capacity load. There may be some distortion.
Yes, there is distortion, but what I am telling is that you have current, for example, you have current distortion in the current, but you saw that it will not cause any power loss, because third harmonics with fundamental voltages does not lead to any active power transfer. So we are not losing anything. So what is the problem? Anyone?
The circulating current.
Yes.
Circulating current, due to third harmonic, circulating current is created, which may be the reason.
Yes, part of it is for sure.
And
it is true.
heat will be also generated, sir. Due to third harmonic, fifth harmonic, or other harmonic, heat will be generated. That's why I think.
That is the coming to that point only. Heat will be generated. How you are telling it will be more problem in terms of heating? Just see, what is I? This magnitude of this current can be written as fundamental RMS. For example, I want to find the IRMS, because heating is from RMS. So fundamental plus third plus fifth, all this will be summed up, and then you find the RMS. So even if the third harmonic current component is not causing any power transfer, but what it is causing? It is causing the magnitude of the overall signal, this signal to rise. And we know power loss is IRMS square into R. So you know that in the transmission lines, when these type of activities happen, when we connect the loads of such natures, it will cause two type of problems. One problem I told you, that it will degrade the PCC, that is point of common coupling voltage quality, because you know that if you have the, for example, the generation, okay, the three phase, and then you have the point of common coupling like this, and you connect the loads. So if you draw this kind of currents, what we know, if such these feeders have some resistance, for example R, then if we say V minus I into R, this is the point of common coupling voltage. So if this R is distorted, then I into R is also distorted. So this PCC voltage becomes distorted, even if from the generation side we are getting stiff sinusoidal AC voltages. So one problem is this, that this current is leading to voltage quality issues. That is, they are complementing one another. But one more serious issue it is posing is that due to this non-sinusoidal nature or non-linear nature of the currents, that is the power quality, current quality problems, it is raising the magnitude of the fundamental of the overall signal RMS component. So this is actually causing the derating of the equipments. What I mean by derating is that whatever power we would have got from the I1 fundamental, that is RMS value of the fundamental component of this current, that was there only. Other than that, we were not getting any extra power, because voltage 50 hertz, current 50 hertz only results to the power transfer. However, these additional harmonic components are raising the amplitude of the RMS current, of the RMS the value of this signal, which is causing actually the derating of all the equipments present. So additionally, it is accompanied with heating. That's why we tell that these harmonic components leads to additional losses. Actually, these are not causing any power transfer loss or something, power transfer issues or something like that. But these additional terms are causing the transmission loss. While transferring that much power, whatever the power I want to transfer, actually these additional harmonic components are leading to power loss in the lines. So that is a major concern and leads to economic implications. Like, for example, you want to transfer 1 kilowatt of power, but your current quality is degraded. Then that additional power loss in the lines are accounted due to this distorted harmonic components. So they have a term also known as distortion factor. That's why we multiply the distortion factor and displacement power factor to get the actual power factor. We will see all those. So these are the implications, right? So also you see that there are some resonance issues as mentioned here. All these things you have already covered, like loss of production, which I was telling, that due to the faults you have loss of production. The switching transients, there are also some, for some cycles there exist some distortions, and that can also lead to damage to household appliances for over voltage and under voltage, because to sensitive loads some kind of that disturbances may also be there. So these another issue is the DC offsets. The DC offsets can lead to saturation in the core of transformer. How we will see, just DC offset, just keep these 3 points: DC offset, third harmonic, and zero sequence. How they are causing the transformers to get saturated. So this is an important point. I will discuss it. And apart from that, you have already told, like voltage fluctuations, all these you know. Frequency fluctuations. Frequency fluctuations can be detrimental for the generators and the mechanical equipments that are coupled to the systems, that is the thermal power plants. They will be detrimental. So these are some of the issues that you face. So coming to the transformer issue, that for example you have unbalance, or you have third harmonic components. So unbalance means you have negative sequence components or zero sequence components, right? Negative and zero sequence components arise due to unbalance, and due to distortion the harmonic components arise. So either may be there or all the three may be there. So what are their implications? Can you tell me on the transformers? Anyone? So how do the zero sequence currents look like? Can anyone tell? The three-phase zero sequence currents, how do they look like? Three-phase zero sequence or the 3 omega, that is the third harmonic currents, how do they look like? Are they DC quantities or AC quantities? Anyone?
The DC quantity, I think.
No, actually these all components, these negative sequence, zero sequence, third harmonics, all are AC quantities. But what is common between them is that don't confuse DC offsets and zero sequence or third harmonic currents. Because DC offsets mean you have a signal, right? Sinusoidal, purely sinusoidal signal. So here, no DC offset. DC offset means no average value of this signal. But if you have DC offset, you get some shift in this AC signal like this. So we have some DC value, which is this one, this much. So this much is the DC value. So we term this as DC offsets. Now, if you have purely sinusoidal voltage, your flux is purely sinusoidal. So some residual flux concept is not there. So the core is getting some phi like this. For example, because if your for example, your voltage is cosinusoidal, then your flux will be sinusoidal, and either ways, because V is N d phi dt, right? Like in transformer you see. So if voltage is sinusoidal, then flux is sinusoidal. But if, for example, you have some offsets in those quantities, then it may lead to saturation of the transformers, because you see how the core looks like. For example, you have a three-phase core, right? So it is a shell type, right? I am drawing. Now you have the primary ABC, and the secondary is stacked upon this. So A and then another set of windings you have. So for example, another A dash winding and B dash winding on top of it to minimize the leakage, and C dash. So can you tell me how the flux path will look like for the A, B and C?
The 180-degree phase shift. Study.
No, actually
In phase shift.
the
120
signals are
degree.
120 degree, right?
120.
So what means by 120 is you have maximum value of flux for one phase. Then the other two phases are negative peak of that, half peak. So minus 5/2 will be there, such that the net flux becomes 0 in the code at any time. Instantaneous flux I am talking about, right? But if you have these third harmonic currents or zero sequence currents, how the zero sequence currents will look like? For phi 0A, that is zero sequence A phase flux, and then again B is also phase shifted by 0 degrees because they are zero sequence currents, and again the B and C. So all these three phases, their zero sequence components will be 0 degrees phase shifted. So these components will actually lead to saturation of the core because they increases phi peak. What is B? B is phi by A. So this actually this core is designed for some level of saturations. However, when the flux increases, then the magnetic flux density B increases, which may lead to saturation of core. So due to their additive efforts in the due to the presence of zero sequence or third harmonic currents, it may lead to saturation of the transformer. And what happens when the transformer gets saturated? Anyone? Hello? Anyone can answer. I want this session to be interactive, but no one is answering. You can answer, we can see the concepts behind these things. Okay, so what is actually the thing is that due to the presence of this zero sequence and third harmonic components, it leads to saturation of the transformer core, and saturation will, you know, the BH curve, right? So when your flux density increases, the current drawn is very high, because B versus H curve can also be written as phi versus I curve, because what is B? B is phi by A, H is Ni by L. So if your transformer is already designed, then the area is fixed, so A is constant, then it is phi, because B is proportional to phi in that case. And H, this N is already constant, so I, it is proportional to I, right? So phi versus I curve. So when flux increases, it draws high level of currents during and may damage the transformer, right? So coming to the next concept, so the techniques for mitigation you have already learned. First technique is designing passive filters. So passive filters means use of reactive elements which supports the these passive filters. They consist of L and C networks, right? So what these filters actually are not responsible for any power loss, active power loss, and they only mitigate for the distortion that is for the harmonic components or the negative sequence and zero sequence currents present in the waveforms. And for one part, and what is their drawback is that the passive filters can mitigate only one particular nature of distortion or particular nature of I can say power factor issue or voltage regulation issue. One particular fixed type of issue it can address. But once that issue changes, for example, the loads change or something in the network change, then these passive filters will not provide adequate performance. So for that, we go to active filters. Active filters are quite efficient in reducing the power quality issues by reducing the distortion in the waveforms, and they can adapt to any scenarios, that is within some operating limits of the devices. It can help in mitigating the power quality issues during various operating conditions. And tuned passive filters are some filters which are specifically designed to attenuate some particular frequency, that is harmonic components present in the signal. So you can see the devices like capacitors, capacitor banks we can use to actually mitigate the voltage quality, that is amplitude. In terms of amplitude, voltage amplitude issues, that may be voltage swell or voltage sag, we can address those by designing appropriate reactors, that is inductors and capacitor banks. And specifically we can also use custom power devices like as dynamic voltage restorers or distribution static compensator or UPQC devices, and also the power filters which I am talking about, like the specific to attenuate the specific harmonic frequencies. We can also use voltage source converters, that is AC/DC converters, to compensate for the harmonic components. Some multiples AC/DC converters, by designing appropriate transformer windings, and appropriately we can mitigate the distortion to some level. And using matrix converters, that is AC to AC without the presence of any DC links. So you can use these devices to mitigate distortion in the waveforms. So coming to some standards, there are standards by IEEE, Institute of Electrical and Electronic Engineer Society. There are one IEEE 519 standards. Recently, the 2022 version has also been released, which talks about the standard limits for presence of harmonic components in the electrical power systems. That is how much actually harmonics you can allow in the grid. So that is limited to 5%. So some standards like that are devised so that the power quality performance of those systems are not below a certain level. And the IEC standard 61022, and this is the international standard for fluctuating loads, and the NEMA WD6 standard. This all you have learned already. So I'm just, for a recall, I am telling you. And these are all the standards that you have already seen in the lecture. So any one of you know about these devices? Anyone used in their labs or something, some research scholars use in their labs?
Power quality analyzer.
Yes, yes. These are flukes and these are Hioki devices which are power quality analyzers, and you have the voltage probes, and these are the AC probes which you can use and feed in the signal information to these devices, and they will tell you how much is the active power, how much is the power factor, how much is the total harmonic distortion, how much is the unbalance factor. All those information you can analyze using these instruments. So these are power quality monitoring devices. So this power quality and harmonic distortion, that analysis that we will be doing in this course, will be useful for smart integration, that is useful integration of the renewable energy dominated inverters into the grid. So this can be utilized to act as a compensating device, active compensating device, to mitigate the power quality challenges, because all these devices draw non-linear, because the loads are also non-linear, and the connected actually the voltage is also subjected to disturbances. So you can use UPQC in that condition, series inverters, to regulate the voltages, and using active devices, that will be practical. And renewable energy impact means that you can use these devices also to process the power generated by the renewable energy sources, as well as compensate for the harmonics. And we can also use IoT and enhanced monitoring, that is remote monitoring actually you can use. So these are the aspects, some of the aspects. So these are some basic terminologies like imbalance, harmonics, root mean square. I think you are acquainted with all these terms and can calculate the RMS value of some signals, or some interruption, temporary interruption, what is the terminology mean, how much cycle. So you can all see this from the lectures. I am skipping this and coming to the So coming to some fundamental concepts now, before solving the numericals, you should be aware of some fundamental concepts, right? So first concept that we will be talking about is that, for example, you have some voltage like this. So I will prefer you can take the notes also, or you can ask the doubts if you have any. But better you can do with me so that it is beneficial for you. So for example, the current is like this, right? So what you can infer from this, both the voltage and current contain harmonics, right? So I think most of you know Fourier series, right? So if this is a signal which is periodic in t, and the voltage signal is also periodic in t, then we can write Vt as some V0 plus summation n equal to 1 to infinity Van, then you have cos n omega naught t plus sigma n equal to 1 to infinity Vbn, some coefficient, into sine n omega naught t, right? So what does this V0, Van and Vbn signify? And what is this omega naught? First of all, you have to note the period of this signal. It is very important that you look at a signal and identify the time period. So once you have identified the time period t, omega naught is given by 2 pi by t. What is omega naught? Omega naught is the fundamental frequency. It is 2 pi into f naught, right? And t is the fundamental time period. Okay. So now, once you have determined omega naught, it is very important for you to perform the Fourier analysis to determine V0, VAN and VBN, because these are the three unknowns. So V0 is nothing but the DC value, which gives you information about the offset present in the signal. So how to calculate it? It is 1 by time period, just mean. So xt into dt. For any signal xt, you take the mean. So for this example, it is vt, so I am writing vt. And since the limit, the dt, so you have to put the limit in t. So t equal to 0 to t. And what is VAN? VAN is 2 by t, integration over one time period. So you may take 0 to t or minus t by 2 to plus t by 2. And then you take the signal Vt into cos of n omega naught t into dt. And VBN is 2 by t integration over one time period Vt into sine n omega naught t into dt. Similarly, you will also calculate the current I0 plus some sigma n equal to 1 to infinity I a of n cos of n omega naught t plus sigma n equal to 1 to infinity I b of n into sine n omega naught t. So any problem up to this? Yes, hello? Okay. So now you see, let us take some example that Vt is sinusoidal, for example. So Vt is something V of Vm, I can say Vm1 sine omega t, and It is Im1 sine omega t plus Im3 sine n omega 3 omega t, for example. So this current has third harmonics and fundamental present in it. Now can you compute the power? What is the power due to this type of voltage, which is purely sinusoidal, containing only the fundamental component Vm1 sine omega t, and the current, which is having two components? After the Fourier analysis, we found that the current is having only the fundamental and the third harmonic component. So can you compute the power for this? Anyone?
Vm1 into Im1.
No, what is the general definition of power? Can you say for a periodic signal? What is the all
V
these two
into I.
signals are?
V
Yes,
into I.
it is P average equal to V into I, whatever you are telling, over one time period, right? And then mean it over the time period. So Vt, It, dt, and then mean it over the time period. So mean is the power. So once you compute that, what you get? Let us go to the next slide. So once you compute that, what you get? Vm1 into Im1, then sine square omega t is the first term. You have 1 by t, and then you are integrating over 0 to t. One term is this. Another term is Vm1 into Im3 sine omega t into sine 3 omega t, right? So this is the power. So this integration you already know. What is the integration of sine square omega t over one time period? If you calculate it, sorry, dt will be there. It is half. So it is Vm1. This is the peak value of fundamental of voltage, peak value of fundamental of current divided by 2. Integration 0 to t, 1 by t sine square omega t is half. So what can we write it as? It is Vrms into Irms, right? And if you compute the integration 1 by t integral 0 to t Vm1 Im3, and what is the formula of sine A sine B? It is cos A minus B, right, minus cos A plus B by 2. So you integrate over cosinusoidal terms. What are the two terms that will be coming here? It will be coming as cos of 2 omega t minus cos of 4 omega t. Integration 0 to t, and by 2 is one factor is there. So what is the integration of 0 to t over cos 2 omega t or 4 omega t or any integral multiple of omega t? What is the value of just integrating over a time period? Like for example, a sinusoidal signal you have. If someone asks you integrating over a time period t, He's asking you to find the area under the curve. So what is the area under the curve? 0. So these two are getting 0. So we saw that there is no contribution to the power for the third harmonic currents, as I told you initially. So what is P? P is VM1 or VRMS into IRMS. How it is coming VRMS into IRMS, clear na? Because these two you can break into root 2 into root 2, and V peak by root 2 is VRMS. Then I peak by IRMS. What would have happened if this problem that I initially gave you is having some shift? Sin omega t minus theta. What would happen? What would there be any change in the power expression? If the current lagged the voltage by theta, will there be any change in the power expression VRMS into IRMS? Then there will be some cos of theta. Then theta is 0, then VRMS into IRMS. Any problem? Any doubt? So another concept that I want to discuss is some terminology you must have learned. Crest factor. What do you know by crest factor? For any waveform you have, for example, let me take a square waveform like this with a period t. For any waveform which is periodic, can you define the crest factor? So crest factor is, if the signal is S, then it is defined as the peak value of the signal over this time period t divided by the RMS value of the signal. Right? You can take it down, it will help you solve the problems, right? So another term is distortion factor. What is distortion factor meaning? This is nothing but fundamental component of the signal under consideration. So S1 RMS, the fundamental component RMS value divided by the RMS value of this signal. So this is the distortion factor. And another term is the total harmonic distortion. What is the definition of total harmonic distortion? It is the RMS value of all harmonic components except fundamental divided by the RMS value of fundamental. So how do you find the RMS value of all the harmonic components that are present in a signal? If you know the individual harmonic components, for example, you know V1, V3, V5 as the RMS values. Note, these are the RMS values, not the peak values. If someone tells you the fundamental RMS value is V1, the third harmonic RMS value is V3, the fifth harmonic RMS value is V5. RMS value means V5 into some sinusoidal term, sin 5 omega t. This is the fifth harmonic. How the third harmonic will look like? V3 into sin 3 omega t, like that. So can you tell me how much will be the RMS value of all the harmonic components? How to compute it? If you know the individual RMS component values, any idea? Yes. So sigma, yes. Correct. So I can write Vn square, n not equal to 1, n being integer, and then root divided by what I am having, RMS of fundamental. So V1. I can write like that. Except the fundamental, I find the RMS value of all the harmonic components, square it, and then sum it, and then root it. And after that, I can also write it as so I am writing here actually. So THD equal to, then it was n not equal to 1 Vn square divided by 1 square. Then what you can write? Sorry, V1, not V1 square. V1 RMS, right? V1 is the fundamental RMS value. So taking it inside the square, what you have? You have Vn square by V1 square. So n not equal to 1 was there, right? What we could have done is, this could have been written as Vn n equal to 1 to infinity square minus V1 square by V1 square whole root over. I can write like this. I just included the first term and then again subtracted the first term. So it is same. Then we can write it as 1 by distortion factor square, because what was distortion factor? Fundamental of that signal by RMS. So what is this? This is RMS square, right? So 1 by distortion factor square will come. This step is clear. Minus 1 is also there, root over. So THD can be written as 1 by distortion factor square minus 1. So now coming to some fundamental concepts like finding the Fourier series for a square wave. So this is known as a square wave, right? Now in power electronics, you will come across this type of waves quite often. So it is important that you know the square wave. But before that, we should discuss that what is the nature of this square wave? Is it odd or even? Anyone? So it is continuous, right? Here also it is going. So it is odd or even? The definition of odd is x of t with a minus, x of minus t if it is, then it will be minus of xt. So you can see there is a mirror image reflection. There shall be a mirror image reflection for this signal about the origin, right? This y-axis. Sorry, about the x-axis, right? So how I determine this mirror image reflection? Any idea? Hello? Yes, can you be louder? Hello? Yes, so it is just a reflection, as you can see, about the x-axis, right? So this signal is odd signal, because if you put t, for any value of t, the minus t is the negate of that. So this is odd signal. So for odd signal, if you want to find the Fourier series, a0 plus an into, that is sum over n1 to infinity, then cos n omega naught t plus sigma n equal to 1 to infinity bn sin n omega naught t. So what is the equivalent signal of odd into odd? What type of signal you get? Anyone? Yes. So odd signal you can consider as minus. So minus into minus is plus. So this is even. So odd into even is? Yes, odd. So odd is minus, this is plus, this is minus. So what is even into even? This is even only, right? So now when you will be finding Bn. What is Bn? 2 by t integration 0 to t, then some signal into sine n omega naught t. So sine n omega naught t is a odd signal. Sine is odd. Sine signal is odd because how it looks like this. So if you multiply some odd signal with some odd signal and integrate it over its time period, then it will be non-zero because it is an even signal. So over the time period, if you integrate it, it will be non-zero for even signal. So Bn for odd signals is not equal to 0. However, An, what is An? 2 by t integration 0 to t, then you have some signal cos n omega naught t. Cos is even function. However, this signal is odd, and I told you odd into even is odd. If you integrate that odd signal over its time period t, then it will be 0. So An is 0. Now what is the DC value of the square signal? A0 is 0. You find the mean value over one time period. How much ever area you have in positive cycle, same area negative cycle. Over the time period, if you sum and average, what is the offset? DC value? It is 0. So for odd signal, A0 and An is 0. So only you have to do the hard work in calculating Bn. And then you are done with the Fourier series. Right? So let us determine Bn for this square wave. So what is Bn? It is very easy to determine. It is 2 by t integration 0 to t over this some signal xt into sine of n omega naught t into dt. Since this is dt, we are putting the limit of t equal to 0 to capital T, right? Now this is 2 by t. Then what is, we can break it, na? Then this is t by 2. Because I am writing it like t and all those, you can also write it as pi and 2 pi. So 0, I can say 0 to t by 2. What is the signal amplitude? For example, let me tell this as A and tell this as minus A. So I can write up to t by 2 it is A, then sine n omega naught d plus minus t, plus t by 2 t, because t by 2 minus, then again sine n omega naught t dt. So this is Bn. So what is the integration of sine n omega naught t? It is minus cos n omega naught t by n omega naught. So n omega naught comes to the denominator and we take a common, right? Then we have minus cos, but we write cos n omega naught t and reverse the limits. So this is t by 2 to 0. Then next term is sine n omega naught t again. Integration is minus cos minus minus plus. So plus cos n omega naught t over the same limits t by 2 to t. This is Bn, right? So if you compute this, your answer will be a by n pi 2 minus 2 cos n pi. Because what is omega naught? Omega naught is 2 pi by t. You put omega naught as 2 pi by t and put the limits of t, you will get it. Because you can assume a circle and n pi, cos of n pi. What is cos? Cos is the x-axis reflection. So cos of pi, if someone asks you, assume this as 0 position and rotate in the anti-clockwise direction. So cos of pi is minus 1. This is plus 1. So if n is odd, then what is the value of this term? Anyone? Anyone can tell? If n is odd. Yes, hello? Yes, I am telling what will be the value of this parameter, this expression, if n is odd. As well as you can tell if n is even. So what I told is that for finding cos of n pi, if n is odd, then you see cos of pi is what? Cos of pi is, you assume a circle and then you take the x-axis reflection to find the value of cos. So if I assume n is odd, what is cos of pi, 3 pi, 5 pi? Can you tell? Just see the x-axis reflection, it is -1. So for n be, yes, okay. So for n being odd, always we are getting the value, this value as -1. So -1 into this 2 is -2 and minus minus plus. So for n being odd, Bn is coming as 4a by n pi. Agreed? However, if n is even, what is the thing? We are getting +1. So this cancels out. Then Bn becomes 0 for n becoming even. So one thing you can see that for this type of square waves, you have no even harmonics. So this type of waveform is known as half-wave symmetric waveform. You can write it, half-wave symmetric. So additional one information we got that for half-wave symmetric signal, there will not be any even harmonic present. But that does not imply if the signal is half-wave symmetric, then the sine or cosine terms will be 0. That does not guarantee it. So I will write two things. Please take it important. It is important. So whether your an or bn terms will be there is determined by what? Is determined by whether the signal x of t is odd or even. It does not guarantee whether even harmonics will be present or odd harmonics will be present. The signal characteristics, whether it is even or odd, will only guarantee whether an will be there, bn will be there, both will be there. You can assume, you can see by calculating the an bn, and we have already shown you without calculating also you can say. But if the signal is half-wave symmetric, you can say maybe an there, maybe bn there, or both may be there. But one thing you can say for sure, if it is half-wave symmetric, that there are no even harmonics. Now this signal is both half-wave symmetric and odd, right? So if the signal is half-wave symmetric as well as odd, we get two information. From odd signal, we can say bn is not equal to 0, other terms are 0. By just seeing the signal, we can say. And from half-wave symmetry, we can say only even harmonics. So n belongs to even will not be there. So this means only odd harmonics. And if someone asks you to write the Fourier series, what will be the Fourier series? The Fourier series will be this coefficient 4a by n pi sigma n equal to 1 to infinity, n belongs to odd only. Or you can write 2k plus 1, 2k minus 1, where k belongs to 0, sorry, k belongs to positive integers, like 1, 3, 5, like that. And then you have sine n omega naught t. Can someone tell me one interesting thing? If this signal was shifted by alpha, what would have been the change in the Fourier series? Yes. So omega naught t minus alpha would have been introduced. However, this amplitude would have been unaffected because the quality of the signal will not change. This is just a shift. So in phase, you see a shift in the Fourier series. And one thing you also please note, this is the RMS value or the peak value. This value, whatever you get using the Fourier series, peak value, correct. So this is very important actually for the course perspective also. Sometimes you do the mistake that you take this as the RMS value, but this is the peak value. So what will you do to get the RMS value? You will do peak by √2 to get the RMS. So I think this is clear. So you can deal with the square waves now, any type of square waves. Now another thing is there, quasi-square waves. So this is a quasi-square wave. So why quasi? Quasi means that for some part of the cycle, it is not there. It is zero. Sorry. So some pulse appears for some duration within the half cycle and again appears within the negative half cycle. But for the other duration, it is zero. So again, can you say whether it is odd or a even signal? Yes, anyone? It is odd, right? Because you see how the signal looks. It will again go like this.
Odd signal.
Yes, correct. It is odd signal. And can you also say that is it a half wave symmetric signal or not?
Yes, sir. Half wave symmetric.
Correct. How will you see half wave symmetry? Just place a mirror here in the T/2 cycle point. Half cycle point. This is the full cycle. Just place a mirror in the half cycle point. See whether this is the reflection, right? Just place mirror here. It is the reflection, right? Negative reflection, I mean to say, right? So because half wave symmetry is half cycle negative reflection. Right? So both are satisfied. So what can you infer? Right? Understood? Now if you find, how will you find Bn? Bn is again same, 2 by 2 pi. For this case the time period is 2 pi, so I'm directly taking 2 pi and just integrate. That is alpha to pi minus alpha. What is the signal? For example, assume this is as a, some a into sine n omega naught t, same like previous, into d some omega naught t, because we are talking about the angles. This is omega naught t, so d omega naught t, and place the angle limits. And again you have only from pi plus alpha to 2 pi minus alpha, which is minus a into sine n omega naught t d omega naught t. So if you calculate, you will get Bn as 2v by n pi cos n of alpha minus 1 by cos n pi. Writing it in a more formal way, Bn, as you can see, so as you can see, for even n pi, what is cos n pi? It is 1. 1 minus 1 is 0. Even are absent, right? So I'm only writing for odd. So Bn can be written in two ways. Bn I can write as 4v by n pi like previous, but now there is a cos of n alpha term. So this is the coefficient, and we have sine n omega naught t and sigma over n 1 to infinity. N belongs to odd. Or this is in terms of alpha. Alpha is this shift. Please note. Now another trait is also there in power electronics, to write it in terms of this d. So I can write like alpha equal to 2 pi minus d by 2. Sorry, 2 pi minus 2d by 2. Why? This is 2 pi. I take away the 2d terms. Sorry, 1 second. Let us do in pi only, right? Let us see in pi. So how much is this much? This is pi. So let us take away this 2d from it. Then divide it by 2. This is alpha. So you just plug it in here and write it in terms of d. What you will get is again sigma n equal to 1 to infinity 4v by n pi sine nd will come into sine n pi by 2. This is the whole coefficient, and then you have sine n omega naught t. And sigma is outside, right? So this whole you have this sigma over. So two forms we just saw. One form is this one. Another form of Bn is this one. So sine omega naught n omega naught t is there, but the coefficients are in terms of cos or sine of this d, and this is in terms of alpha. So both, can you infer one thing? What will be the, for this case, if alpha is 30 degree, what is B3? Can anybody calculate? So n is 3, alpha is 30 degree for this example. So what is cos 90? Yes, so for this kind of waves, you have no third harmonics. Right? So this is will be helpful in the when you will be solving the problems. So I think you have taken down, or I can wait. If someone is taking down. Done? Yes, so now I will be moving on to the, now you are equipped with all the tools that we will be using for the solving the numericals, right? So the numericals, I have taken almost all type of examples that you will be solving, and we'll also be learning the concepts, and then you can solve easily the problems that are given in the assignments, right? So let us start with the first problem. So same, we see that we have a square wave, current amplitude of 20 amperes. So can you calculate the crest factor? I already defined the crest factor. It is the peak divided by RMS value, simple. So what is the peak value of the square wave? For example, let us assume this is A, some amplitude A. This is minus A. So what is peak? Peak is A. RMS? RMS is nothing. You square the signal. How to calculate RMS? Anyone? First step is? Step 1 for calculating RMS value of a signal. First step, square the signal. Then sum and mean it. Mean the signal. That is, take the average. And finally, you take the root. So if you square the signal, mean it, and then take the root, you will get the same signal, however, with this constant amplitude. So this is A X RMS. This is A. So same A. So this is 1 crest factor, right? And the distortion factor is defined as, anyone remembers distortion factor?
S1 RMS divided by SRMS.
Tell RMS by RMS.
Correct. For any signal, S you take divided by SRMS. So what is the, just we calculated fundamental RMS? Anyone recalls? 4 into A by pi. However, this is the peak. So we had to divide by root 2. Divided by RMS value we just calculated is A. A goes away. So 2 root 2 by pi. Please remember this. For a square wave, the distortion factor is 2 root 2 by pi. So what is 2 root 2 by pi? It is 0.9. So you see the distortion factor is independent of the amplitude of the square wave. Anyone, the crest factor also, the distortion factor also, and also the total harmonic distortion is independent of the amplitude of the square wave. Because all these parameters denote the signal quality and are invariant of the amplitudes. So now you calculate the THD. THD is 1 by distortion factor whole square minus 1 whole root over. So what you are getting? You will get 48.34%. It was easy, right? So same coming to the now quasi-square wave version. So quasi-square, someone remembers what is the crest factor? Crest factor is defined as peak by RMS. Some signal S maybe. So what is the RMS for this? For this type of signal? So when you will be squaring it, you will get this and this contribution. Now you want to mean it. So what I did, I squared it, A square, and into dt, time was there. So 120 plus 120. Because for this 120 degree, we are getting contributions. For this 120 degree, we are also getting contributions. But we want to mean it over the 360 degree and then want to take the root. So, because also you can write it as A squared into 120 by 180. Because when you will be squaring it, this part positive half and negative half will be same when you will be squaring this signal. So either way is correct, and it is coming as root over 2 by 3 into A. This is SRMS. Understood this approach? So you find the spread, I can say the spread of this or the contribution, mean it over the symmetrical period, and then root it to find the RMS value and multiply it with the amplitude. So this is the SRMS. This is a short way of calculating the RMS quickly. So now when you plug it in, the peak is A and this is root 2 by 3A, which is coming out as root 3 by 2, right? So it is coming out as 1.224. So first is 1.224 crest factor. Now they are asking the distortion factor and the THDs. So B part, distortion factor in terms of percentage also you can, if it is not asked in terms of percentage, don't give the percentage. Into 100% you don't do if they're not asking. If they're asking for percentage THD, then give in terms of percent, or you don't give percentage. If only it is asked, then give the percentage. So distortion factor is what? Distortion factor is I1 RMS divided by I or S RMS. So it the fundamental is 4A by pi cos n alpha. And the RMS is root 2 by 3 we calculated. So what it is coming? So there is a 1 by root 2 because this should be the RMS. So for fundamental, n is 1 and alpha is 30 degrees. So cos 30 means sin 60. So root 3 by 2, 4 by pi into 1 by root 2. What it is coming? So this A gets cancelled into, okay. So what it is coming? Anyone doing? Hello? If anyone does, can tell me the answer. I want to see at least one or two of you solving. Otherwise, this will not be helpful. So you can calculate it, what it is coming, 4 by pi divided by 2 into root 3. What is cos of alpha is there into cos of alpha is 30 degrees, right? So it is coming around 0.955, right? So what is the THD? Please, I will suggest do with me so that you can get the practice out of it. Because if you practice here, you will not have any trouble in solving the assignment problems, right? What you are getting here? 31.08%. So it is more closer to sine. As THD is low, what it indicates? Waveform is more close to sine. So a quasi-square is more closer to sine wave than a simple square wave. Coming to the next problem. So they are giving AC single phase AC voltage controller to heat for some heating applications. So for heating applications, you need to have the dissipation of heat. For that, you have resistive loads because inductor or capacitor cannot dissipate heat. So you need dissipating elements. So we have modeled the load as resistance. So anyone have some idea about AC voltage controller, how the waveforms will look like, how they work?
Both positive pulse and negative pulse will be getting in the output based on applied gate pulse period.
Yes, applied firing angle actually.
Firing
So
angle.
you actually use in your fan regulators also this kind of thing where you have used it for low rating applications using the triac. So just for high power rating applications, we use such single phase AC voltage controller using the thyristors. So by controlling the alpha, you can actually change this RMS value. However, you cannot change the frequency of the voltage. For changing the frequency, you need some cycloconverters, like that kind of thing. However, it is only limited to changing the RMS value, the amplitude actually of the signal. So how can you draw the waveform? So see, this was a simple AC source, right? Like a single phase supply. So how it looks like? You can do with me, right? I will give time, you do with me, right? Because only solving the numerical is not the purpose of this session. It needs to be have an interactive thing so that you understand the concepts. Numerical will anyway be coming if you understand the concepts. So now I apply the pulse here, okay? So tell me, if you have this applied over the gate pulse, the firing, the pulse is fired for this thyristor, for example, this is T1 and T2. Now this is, for example, the polarity. Now I fire T1. So what kind of voltage will appear across the load? Where I will stop? Pi minus alpha or pi?
Pi.
Anyone? Yes. Why pi?
Pi.
After pi, why it will stop? Because the load is resistive and the voltage is reverse appearing negative after that. So the thyristor, this T1 will be reverse biased. So this stops. However, next thyristor T2 is fired, which makes the conduction happen through this path. Right. So as soon as this is fired, what kind of voltage will appear across this load? V0. So where I will stop now? Again 2 pi. Now you see, if I delay the firing mode, the RMS value of the voltage will keep on reducing, which is actually desired for this kind of applications to regulate the voltage RMS value. Now you see this is 80 volts RMS, they are already telling you. Now they are also giving you the power. Now you see that this, for this kind of numericals, if someone gives you the power at the load side, it is easy to determine the fundamental components. Why, I will show you. You know the power balance, right? So input power. Acha, before that, let me finish the drawing the waveforms. How will the IS look like? Before that, you tell me how will I naught look like? I naught is V naught by R. How will I naught look like? Just be loud, please. Yes, correct. So because it is a resistive load, only it will follow. I can minimize its amplitude little bit. Yes, like this. Now, what will be the source? This is the load, and source current, how will it look like? IS. Same, right? Yes. Because the conduction is just forming through this or this path. Anytime you see, then the conduction is forming apart from these intervals. Other than that, both, when the source is not able to send current, load is not able to get the current, because it is a resistive load, remember, not an inductive load that can hold the current and have some paths. So the input power and output power are always equal. So if you equate, then what you get? Any idea? What is the output power? 800 watts, right? So what is RL? V RMS square by P. What is V RMS square? 80 into 80 by P is 800. So what is RL? 8 ohms, right? So what is I naught? I naught is simple. P by V. You did not have to calculate RL. If it was asked in the problem, I am solving extra. Okay. You just solve what is I naught. I naught is 10 ampere. This is the RMS value, remember. Because from power and voltage, these are all RMS quantities given. So you get the RMS current only. And you know I naught RMS, output RMS and input RMS are equal. How you know that? By power balance. So output, because by KCL also you can say, right? I naught RMS and supply RMS are same. So what is supply RMS? 10. Now if the feeders have a resistance of 0.1 ohm, what is the loss in transmission? Now you have a positive rail and a negative rail. Okay, so loss I can say is 2 into IS square, which is IS RMS square into R. R feeder is 0.1. So 0.2 into what is 10 square? So 20 watts. This is the answer. Yes. Yes, see the feeders. You see this is one feeder and this is another feeder. You have to feed the power, right? The current will go through one path and return through another path. Okay. You can think it like positive rail and negative rail. So by going, the current is incurring this much. Now feeder conductor. Now for the positive feeder, it has this conductor, so which is given as 0.1, and the return feeder you can assume it has 0.1. So resistance is 2 times, right? So IRMS square into R total. R total is 2 times the positive and negative sum, that is 2 times 0.1. Okay. Now I think the losses are then calculated, because loss, whenever you hear, you use RMS. Calculate the RMS current. If power is given, no need to analyze the waveform. Fundamental RMS current you can calculate. Now what we are calculating, fundamental RMS or what? Can anybody tell me? Signal RMS we are calculating or fundamental RMS we are getting by this? From power, if somebody tells you the power and you calculate the source RMS current, what is that? Total RMS current or fundamental RMS current? Anyone? Yes, because I told you that for other harmonics, the power transfer will not be there. So from power, if you are calculating the RMS current, it will always be fundamental RMS. So that's why we are getting the fundamental RMS. And using fundamental RMS only, you need to determine the losses. So coming to the next problem, this is easy problem, I think. So yeah, you have heard of Fortes theorem, right? One second, just give me 1 minute. Lost the charge. Meanwhile, you can tell me how can you solve this problem? The positive sequence power component they are asking. Yes, so you will do symmetrical component analysis, right? Yes. Yes, just we will charge it a little bit. Just 1 minute. I think it is okay. So symmetrical component, what I was telling, just 1 minute. So for a signal, this signal may be voltage, current, flux. Okay. For a signal S, I denote SA, SB, SC as the 3 components in ABC frame. Then it can be written as 1, 1, 1, alpha square alpha 1, alpha square 1, and then you have the S positive, S negative, and 0 sequence. And reverse, how will you write? It is coming as 1 by 3, 1 alpha square, 1 alpha square alpha, 1, 1, 1. So both are useful, right? To go back from one frame to another, symmetrical frame to ABC frame, right? Now you see, what is power? Power is P plus JQ. So how to calculate power? Power is VA IA conjugate plus VB IB conjugate plus VC IC conjugate. Why I am denoting like this? These are all AC quantities, so small letters should be used, right? Now conjugate. So you can also write this as like this: VA, VB, and VC in a matrix form, just like representing, and like this. So I can also write it like this. Clear? So now this matrix I can transform to symmetrical components, and this matrix I can also transform to symmetrical components, symmetrical frame actually, ABC to PN0. If you do that using these two matrices, you find P plus JQ equal to 3 V positive I positive conjugate plus 3 times V A negative I A negative conjugate plus 3 times V0 I A0 conjugate, right? And then when you try to break this, then what you get? You get 1 by 3 VA plus alpha VB plus alpha square VC and IA plus alpha IB plus alpha square IC conjugate. So in simple term, you just remember that P1 plus JQ1, that is positive sequence power component, is 1/3, because a 3 will come from here and a 3 will come from here, and this 3, when you do 1/3, then 1 by 3 will be remaining, right? So 1 by 3 into VA plus alpha VB plus alpha square VC into IA plus alpha IB plus alpha square IC whole conjugate, right? Any doubt? So this is the thing they are asking you to determine. So alpha is 1 angle 120 degrees in polar form. And when you do the conjugate, the angle becomes negative. Okay. So what is the answer that you are getting for this data given? Anyone calculated? Just calculate using this formula and tell me the answer. You can use calculators. Simple. VA plus alpha VB plus alpha square VC multiplied by IA plus alpha IB plus alpha square IC. Then you take the conjugate and then 1 by 3. In per unit you need to do. So I have the answer with me. I will be writing it. It will be coming 1.55 angle 3.88 in per unit. So you can solve and check. Okay. Similarly, in the next question also they are asking you the negative sequence components. So for negative sequence components also same. P2 or Pn we can write plus JQN equal to, the formula remains the same, 1/3 VA plus alpha square VB plus alpha VC IA plus alpha square IB plus alpha IC and then you have the conjugate. So one difference did you note? The previous formula and this formula, there is a one small difference. Anyone note? I am writing the positive sequence formula also here for you. P positive or P1, just writing it.
The alpha square value.
Yes, one small difference is there. Because you know that alpha and alpha square will interchange, right? For positive and negative. Just remember like that. Because the rotation of the positive and negative are opposite. So alpha, alpha square, if you reverse, other than that, no change in the formula. Formula remains the same only. But in the sequence transformation matrix, you can see that alpha, alpha square changes their position. So just remember that among this negative, this positive and negative sequence component has alpha and alpha square interchange. So you can write down the formula. And the answer for this problem I am writing. I have the answer with me. So answer is coming 0.0. 1 second. Just apply this formula and you can just get the answer, right? It is direct question. No analysis is required. So this is the answer. And this is the expression for positive sequence power. And this is the expression for negative sequence power. So can I go to the next problem? Okay. So similar question you have that the single phase AC voltage controller, we have already drawn the waveforms. You just apply 2 into I source RMS square into RL. That is R feeder, we can tell. Right? So IS RMS you apply and then you get the answer. Answer I am writing because same question, so we will not do it once again. It is same only. So answer I will write 2 into 22 square into 0.1. Why 22? Because 50 you have the power divided by the VRMS. So you get the IRMS. It is 22 amperes. So I load RMS you have. So I naught RMS equal to I source RMS because I told you the logic. So since those two are same, so we can write I source RMS because the losses will happen in the feeders and into 0.1. So this is coming as 96.8 watts. If any doubt is there, you can let me know, right? So coming to the next problem. Now there is a single phase fully controlled bridge converter and the alpha is 60 degrees. So there is a continuous load current. So highly inductive load with RL, as you know that the current is continuous. So I naught is continuous, right? It is 30 amperes and alpha is 60 degrees. So displacement factor they are asking and power factor. So power factor, you know, power factor is displacement factor or displacement power factor, which is known as DPF into distortion factor. So first let us draw the waveforms. Everything will be clear after that. So how is VS? VS is like this. But remember, this is a constant load, constant current load. That is continuously, it is drawing constant amplitude current. So V naught, what is V naught? How will V naught look? If I fire the thyristor pairs at these positions, so at the positive half cycle, T1 and T2 will conduct and will impress the voltage V0, VS plus VS. Okay. So it will continue here, go up to pi. Will it stop at pi? Will the conduction stop at pi for T1 and T2? Anyone? Hello?
Yeah, no stop at pi.
Because the current will not allow the thyristor to turn off. So T1, T2 still remains on. So if T1, T2 still remains on, the positive voltage is applied across V0. So V0 is for following the VS. However, when a second pulse is applied, you are forcing T3, T4 to on. And inherently, when T3, T4 is on, and you have not applied the pulse to T1, T2, then it forces the reverse polarity voltage to appear across T1 and T2. You can check by Kirchhoff's voltage law that if T3 is conducting, you can use this loop and you can see that T1 is getting the full reverse voltage of the source. So T1 and T2 immediately turns off. But as soon as T1 and T2 immediately turns off and T3 and T4 starts conducting, what kind of voltage is it impressing across V0? It is minus Vs. So Vs was like this. So minus Vs was like this. Getting my point? So how is IS? When T1, T2 were conducting, current was flowing like this. Just see the path. So which direction it was? This direction. Show by red color. Now when T3, T4 are conducting, what is the path? But current direction is downwards. So what is the current direction of the source? This side. So it is opposite, right? So current direction is reversing, but will follow this. So how is the current looking? From alpha to pi plus alpha, right? The current is flowing, following this, carrying the load current. And from pi plus alpha to 2 pi plus alpha, it is like this. So how much is the conduction path, conduction angle? How much time it is conducting for? Pi. And minus pi duration, and then again pi duration in the negative. So this is how source current looks like. Clear? So it is a square wave, as I told. You have identified the waveform. It is a square wave. So what is the displacement factor then? Displacement factor is nothing but cos alpha, as I told you. Because you know that if a square wave is shifted by alpha, I told you in the initial few concepts that sine n omega naught t minus alpha would be there. Then in fundamental, what is the significance of displacement power factor? Voltage fundamental, current fundamental. How much is the shift? So that is alpha. So cos of alpha is the displacement power factor, which you normally tell as power factor for the linear signals. And into the distortion factor. What is distortion factor for square wave? It is I fundamental RMS divided by I RMS. So what is the I fundamental for square wave? It is 2 root 2 by pi, and I RMS is nothing but this amplitude. So I am assuming. So it is 2 root 2 by pi is the distortion factor, and displacement is cos 60. So cos 60 degree, what is that? 0.5, and you know this is at 0.9. Distortion factor is 0.9, right? So what is power factor? 0.9 into your displacement power factor, which is 0.45. Is it clear?
Yes,
So
sir.
it is
Yes, sir.
like this. The problems are there. Only you need to identify the waveforms, and then you can carry on the analysis. So next problem is with the RE load. Okay. Have anyone solved this? So same the RMS, the signal is there, and now we have a battery. These I am drawing minus Vs for reference. So this is E. So you know that if this voltage V0 is greater than E, only then the current I0 will be in this direction, because the uncontrolled bridge is there, right? So there is no firing angle alpha. So I have denoted this alpha, but this you can write it as theta, right? Don't look it like that angle. It is not the firing angle because there is no thyristor here. So it is the theta, which is the intersection angle of V of t with E. Just assume like this, okay? So these are all theta. So since these can only carry the current in the forward path, even if this conducts or if this pair conducts, only the forward current is allowed, then your conduction will happen only when the voltage is greater than E. So I identify the zones where voltage is greater than E. This part voltage is greater than E, right? However, when the other pairs are conducting, then the voltage is negative of the Vs. So this voltage. Any doubt? So what will be the output voltage looking like? Output voltage will look like this. If output voltage is looking like this, then when there is no conduction happening, then the voltage is, when I naught is 0, what is the V naught? Anyone? When I naught is 0, what is V naught? Anyone?
E. E.
Correct. So V naught is E in situations when no conduction is happening. So what is I naught? If I want to draw I naught is this V minus E by R. So here it is like this. And when no conduction is happening, it is 0. Again, from pi plus alpha, it is starting like this. So now I want to find the average and RMS. So how will the source current look like? Just I told you, in the positive half if it is like this, in the negative half it is opposite. So it will follow this, however it will be opposite here. So you are asked to calculate the supply RMS and its fundamental current. Any idea how to do? So average you can calculate, right? It is from theta to pi minus theta 1 by, what is this angle?
Pi.
No, you see, correctly see. What is the time period?
Pi minus 2 theta.
No, what is the time period?
Period.
Time period is pi only, right?
Yeah.
So then you have this signal. What is this signal? V sine omega t minus E by R. Into dt. This is the average value. And what is the RMS value of this complete signal? So this is also 1 by pi integral pi minus theta V sine omega t minus E by R. You square, you mean, and then you root, right? It is the total RMS, not the fundamental. But what is being asked? It is asked as the fundamental RMS current. So first you calculate I average and I RMS of the total signal. Then I will tell you. So I average expression I am writing down 1 by pi RT 2 VM cos alpha. Please write it down, it will help you. Okay. 2 E alpha minus pi E, where E is battery voltage, VM is maximum supply voltage or peak supply voltage. RT, what is RT? RT is RL plus 2 into R feeder. 2 times R feeder, because positive and negative rails will be there, right? Sorry, here will be the positive and negative rails of the supply. So load resistance plus 2 into R feeder. This is the R total. So we find the average value which is being asked. The first question, it will come out to be 6.37. Please check the answer once. And I RMS of total signal will come out as I 1 by RT. RT is I RL plus 2 times R feeder. So how we will find out this R? R is given as 1 ohm. Okay. So what is RT? RT is, so R feeders are 0.05. So 2 into 0.05 plus 1. So it is coming out as 1.1. E is given in the question as 290 and 230 is the supply RMS. So this is VRMS and VM is 230 into root 2. Is it visible?
Yes, sir, visible.
But this is not appearing here.
Yeah, now visible, sir. Now visible.
Now visible, na? That's what. So this is there. You plug it in these values here in this formula I average. So what is I average? I average is the load average current. And RMS current of the total, that is total RMS current we are calculating, not fundamental. Then we'll see how to calculate. So this is 1 by pi V square plus, when I write as V means RMS. Okay. V square plus E square into pi minus 2 alpha. Okay. Plus V square sine 2 alpha minus 4 root 2 V into E cos alpha. So 1 by 2. RT is outside. Okay. So if you calculate, it is coming as 12.77. Now, let us see what information is given here. The feeder conductors have resistance this much. Okay. And what is asked? Calculate fundamental RMS current in ampere. Okay. Okay. So can you find the power? Because whenever I told you that RMS current, RMS fundamental is asked. Now I calculated RMS only. Now RMS fundamental, whenever they ask, you need to go with the power approach. So first calculate the power. What is the power that is being drawn from the mains? So calculate power from mains. So it is 12.77, that is IRMS square into R total. What is R total? 1.1 plus battery will be charging with this average current. So battery is E into I average, not RMS. Got this point? What I am telling? This is I RMS of total signal. That I RMS squared into R total. That is the power. Loss plus the power that is fed to R. And the battery power is E into I average DC. So I average I already calculated 6.37. E is given as 290. R total 1.1. I RMS total is 12.77. So this is coming as 2026.68 watts. This much power is drawn from the AC mains. Now from the power approach, there will be the fundamental RMS calculation. So I supply 1 RMS. What is that? Since it is a RE load, unity power factor, so, and power we already have. Sorry, not unity power factor, because the power factor will not be unity here, because your current is having distortion, right? But since you have the power already, then you can calculate, right? Power by VRMS is IRMS. Always it will be true, even with or without any harmonic distortion, right? So you get the fundamental RMS. So what is the power? 202.68 divided by VRMS. What is VRMS? VRMS is 230 volts. It is given, right? So what is I fundamental RMS? I fundamental RMS is 8.81 ampere, right? Now coming to another problem. I hope you have 15 minutes time. 7:15 we can take it up to.
Yes, sir. Yes, sir. Yes, sir. Okay, sir. Okay, sir.
Okay, we can extend it. So what I was saying, yes. Controlled bridge converter is there, right? So it is fired at 60 degree and draws constant current. So let us draw it. Now you see, when A phase is under conduction, either T1 will conduct or T4 will conduct. If B phase is under conduction, T3 or T4, T6 will conduct. C, T5 or T2. Now you have the VAB, this one, VBC, this one, VCA, this one. And if we take the negative of this here, this is VCB, negative of this blue one, this will come on top. This is V, CA was there, blue one, negative one was AC, and negative of this
VBA.
yes, the charge, actually the charge fell down, so just give me 1 second. Yes, so this is VBA, right? This one. So now you see, every 60 degree I am drawing the line, right? This is VBC only, right? This is VCA. So you understand, right? So now you see that whatever be the highest this pulse, the conduction is decided by this. So C and B, right? So C and B means C top one, so T5 and B bottom one. So B bottom, because the applied voltage is reverse biasing this one, or top one, and forward biasing this one with the negative voltage. So T6. Then you have T1, T6. Then you have T1, T2, T3 and T2, T3 and T4 for BA, and the final is T5 and T4. This cycle repeats, right? Now, since this is controlled, you have to give the pulse. So that I am not showing, just seeing the conduction, right? Because for 0 to 120 degree, if I see, then alpha to 120 plus alpha will be there for controlled and uncontrolled. This is for uncontrolled. This is for controlled. So who will be conducting during this two time? This T6, right? So when T6 is conducting from alpha to 120 plus alpha, and since the current is this constant current, right, of 30 amperes, so you attach a current source, you model it as a current source. Then again you see where T3 is coming. T3 is coming because T6 and T3, these two are responsible for B phase current, right? So positive half is carried by which one? T3. So T3 is coming here and T6 is coming here. T6 responsible for negative half and T3. So you can assume the waveform shape, right? Quasi-square. Here there is no neither T3 nor T6 for these 60 degrees. And again for these 60 degrees, there is no T3 or T6. So for B phase or for A phase, you do and see it is a quasi-square wave where you have, for example, 0 to 120, you have the negative half, and then 60 degree blank period, 120, then 60. Then you have again the positive half for 120. So this is 180, right? And then again from 120 and 60 degree blanking. So this full is 360 set. This is 60. So you can understand that if someone wants to find out the RMS, then what will it be? 120 by 180 whole root, as I told you. For symmetric, this is symmetric, right? Once you square. So I am taking up to 180 degree, and out of that 120 is conducting. So root over that into the signal amplitude. So what it is coming? Root 2 by 3 into A. This is IRMS. IRMS, right? Of total signal. Now you also know the fundamental, right? So what it is asking, that we need to find out the ratio of losses with and without compensator. Now I can say that with compensator, right? without compensator. First, let us see. Without compensator, you have losses I square RMS total signal into R into 2. These are the losses because into 3, sorry, because there are 3, right? 3 feeders. This right. So what is the this current IRMS? IRMS you can calculate from root 2 by 3 into constant amplitude of 30. So this is what is coming as 24.49. So 3 into 24.49 square into R. R. What is the value of R? It is 0.5. So it is coming as 900 watts. Now this is the loss that is happening. Now with compensator, right? With compensator, what it is doing? UPF, unity power factor at the supply side. So you apply power balance, 3-phase power balance. That is total power balance. What is the input side then? Once it is unity power factor and fundamental, VRMS IRMS 1 into 1. This is input side, right? Equal to output side. Output is V naught average into I naught average. Now, what is the average voltage for a controlled 3-phase rectifier? 3 root 3 Vm by pi cos alpha. You remember this? It is very helpful while deriving. Into I naught average. I naught average is constant current, 30 amperes. And this is VRMS 1 into IRMS 1. Because the compensator solves the problem of harmonics and power factor at the input side. So after compensator is VRMS 1 into IRMS 1. Now I want to find IRMS 1 at the supply side. So VRMS 1 into IRMS 1 power is 3 root 3 Vm by pi cos alpha. This is V naught average and this is I naught average. So power balance just. So once you do the power balance, then one second. Once you do the power balance, what is Vm? Vm is per phase per phase peak. So Vm phase peak voltage, right? So Vm can also be written as root 2 times Vrms because peak is root 2 times Vrms. So Vrms gets cancelled and you find by power balance technique the fundamental RMS value as 3 root 3 by pi cos alpha into 30 degrees into root 2. One root 2 factor is also there, right? And this is 3-phase power, so 3 is there. You did not tell me. 3-phase power, right? Per phase VRMS 1 into RERMS 1 into 3. So 3 and 3 will get cancelled, right? So these 3 will go away. So it is coming as root over 6 by pi, okay, into cos alpha into 30. So this is the fundamental RMS. So what it is coming as is 11.7 after compensation amperes. So after I am writing here, after compensator, same formula, but I amplitude is reduced due to mitigation of the harmonics and other phase lags by the compensator. You have now unity power factor with sinusoidal current at the input with reduced amplitude due to mitigation of the harmonics. So same, but power will be less in this time. So this is now 205.34 watts. Initially it was 900 watt. What was the ratio? 900 divide this. This much you get less power loss. this time. Power loss is reduced, right? So the answer is actually coming as 4.38. Okay. Any doubt? Any doubt?
No, sir. No, sir.
Okay, so one question was remaining. I think we can solve it in the next class, and I will also make you see some MATLAB simulations also, what these nonlinear loads mean and how you can do those simulations. So I think those will be helpful. But for today, I think it is more than enough for solving the numericals. You can also try and let me know. So I will give my email ID. Okay, if you have any doubt, you can mail me. So and I am also planning to form a WhatsApp group also. So I can just form it and then send you the link in the chat box. So I think we can. There is a discussion forum, but I want it to be interactive, so you can join the WhatsApp group. Just wait, I will share the link right in this meeting link only. So let me form the WhatsApp group. Yes, I have formed the group. I will just share the link with all of you. So this is my mobile number also. You can send me a message if you have any doubt or post in the group, right?
Okay, sir. Noted, sir. Noted.
Just sharing the link, right? And join the group and have any doubts cleared if you have. Yes, can you please be little loud or type in the chat box? I am unable to hear you. Hello? Yes. What are you telling? Yes, yes. I will write it bigger, right? I will write it in a, I guess, new slide. Visible?
Yes, sir.
You
Visible,
can
sir.
join the
Visible.
group. Yes, you can join
Join,
the
sir.
group.
Join.
Better
Okay, sir.
yes, better we discuss there because everyone can post their doubts and we have a live. We are discussing in the live. But if you have some doubt, you can post there also. You can get your doubts clarified, right? That will be better, I think. More interaction means your doubts. All of you can see your doubts and can ask me questions, right? I can clarify
Sir,
them.
small doubt, sir. Sir,
Yes.
small doubt.
Hmm.
Sir, every week we have sessions like that, every week, every Sunday.
Every week, actually, the sessions are designed for every week, 12 sessions
Okay.
for 12
Okay.
weeks, such that you get help in solving the assignment problems as well as understand the overall course contents. If you have any
Yeah,
doubt, you
sure,
can.
sir. Sure.
So that
Should
will help
definitely,
you
sir. Definitely.
solving
Okay,
yes,
sir.
solving the problems, right? You try more problems. I will also share some more problems in the group. You try to solve them. I can also share the answers. You solve them and see. If you face some difficulty, like in drawing the waveforms, you can just ask in the group. Maybe we can have those doubts clarified, right?
Okay.
Because for the first and second week, waveforms are important. Waveforms and phasor analysis. After that, more advanced topics are going to come. I think, I think you have joined the group, so right? Or you can share the link with your friends if there some of you are attending and they are not attending this session. So I will end my session here. So thank you. And one
Thank you.
question
Thank
was
you. Thank you.
that I will solve in the next session, right? Okay.
Okay, sir. Okay. Okay. Thank you, sir.
Thank you.